Vennligst reis opp.
Please sit down. Good afternoon, and welcome to this public defense of the thesis entitled Development of Physical Performance in Adolescent Team Sport Athletes, Influence of Age, Sex, and Maturation. Today's candidate, Lars Martin Tingelstad, completed his thesis in August 2025. Based on a proposal from the Department of Physical Performance, the Committee for Research Education has appointed the following committee to judge the thesis and other requirements for the award. Professor Anne Marte Pensgaard, Norwegian School of Sports Sciences, the chairperson. Professor John Oliver, Cardiff Metropolitan University, United Kingdom, first opponent. And you can see up there, welcome. And second opponent, Associate Professor Hilde Stokvold Gundersen from Western Norway University of Applied Sciences. And the committee has concluded that the thesis meets the standards worthy of a public defense for the award of Doctor of Philosophy, PhD in Sports Science. Earlier today, the candidate has given a trial lecture with the title, The Effect of Strength and Conditioning, Training on Physical Performance and Sports-Related Injuries in Adolescent Athletes, How Knowledge Can Be Applied by Practice. The trial lecture has been found satisfactory by the examination committee. So I would now like to ask the candidate to introduce his doctoral research in the form of a short lecture, and the opposing members of the examination committee to engage the candidate in a defense of the work. Should members of the audience wish to ask questions relating to the research, I ask to bring this in written form to the attention of Anne Marte, the chairperson, in the break prior to the second opponent's questions. So please, Lars Martin, the stage is yours.
Okay, this works. Nice. All right. Dear Rector, Committee, family, friends, and colleagues, it was a great pleasure that I can finally welcome you all to this defense of my PhD thesis. And thank you to the committee for both approving the trial lecture, as well as finding my thesis worthy of the defense. For the next 30 minutes or so, I'm going to try and present to you what this thesis contributes to on this topic. Now, in this picture, it might just look like someone brought their older or younger brother to a match because they were one short. But in fact, this is from a game between two under 15 teams, and the scenes like this are far from rare. In fact, in youth sports, it is common to see two players of the same chronological age looking like they belong to two completely different age groups. This is due to large variations in how we grow and mature during adolescence. As you can see here, it can be up to as much as 5 years difference in biological age in a given age group. This means how far one has progressed towards a mature adult state. This will also strongly influence our physical performance. In elite senior sport, team sport, well-developed physical qualities are crucial for performance. It requires frequent, high-intensity efforts, such as sprints, accelerations, decelerations, jumps, and more. So it is important that we prepare our youth athletes for these demands. And to do so efficiently, we first need to understand what happens in the body during this period. During adolescence, both boys and girls go through rapid growth and major physiological changes, and typically peak in the growth rate around year 11 for girls and 13 for boys. So girls mature somewhat earlier, but boys experience overall greater total growth. And this figure from Portuguese Football Academy perfectly illustrates just how much individual variation in timing and tempo of growth varies. So you can see that the tempo varies from short, intense bursts to slower, more extended periods. You know, athletes that mature and grow quite early during this period, the green lines here we are on time, and then you have the blue lines where the athletes who mature much later during adolescence. When it comes to body mass, we see a similar picture. So boys gain overall more body mass, but importantly, they gain more lean mass, which is driven by stronger rise in testosterone. Girls, on the other hand, have much greater accumulation of fat mass. And these differences between sex and growth, especially a larger increase in fat-free mass in boys, will also strongly influence how their physical development progresses during this period. So we know that physical performance here for non-athletes with muscle strength on the left and sprint time on the right both progressively improve during this time. We see this both in non-athletes as well as track and field athletes. This is mostly due to biological development. Before puberty, boys and girls show similar rates of improvement, but around the age of 14, especially when boys enter their puberty stage, girls tend to plateau their development while boys continue progressing. However, only a limited number of studies have actually tracked girls longitudinally, and even fewer have compared boys and girls in the same study using the same testing protocol. This led us to explore these patterns in more depth using 3 complementary angles. We performed a systematic review looking at what is currently known about the development of anthropometric and physical performance characteristics in adolescent team sports athletes across age and sex. We follow this with a cross-sectional study where we looked at age and sex, age group differences and sex differences in physical performance and anthropometrics, and also how maturation status influenced this. And finally, we brought this together to look at how anthropometric and physical performance develop longitudinally across 2 years, using the same cohort, and also try and see how maturation influences this development. Now for paper 1, systematic review, we began by doing a comprehensive search of various databases, and we identified just above 4,000 relevant papers. After removing duplicates, the rest was then screened based on title and abstracts before screening the remaining papers against a predefined inclusion criteria, ending up with a total of 176 studies. Of all of these, both cross-sectional and longitudinal, almost 90% included only boys. 8% included girls, and 7% included both boys and girls. So you can see that there is a large scarcity of studies including girls on physical development. Before discussing the key findings, just want to highlight a few elements in the figures. So below the x-axis, you have the sample size for each age group. Whenever there's dotted lines in the graph, this means that 3 or less than 3 papers were included for a given age group. And we calculated the average yearly difference between age groups, and we used mainly the 12 to 16-year age groups, as this was the one we had the most data on. So what we can see is that for height and body mass development, boys had almost double the yearly development compared to girls. And the fastest development occurs in early adolescence, which also aligns with the timing of peak height velocity. When it comes to physical performance, there was a huge variety in the number of tests used to measure the various physical performance characteristics. So we ended up standardizing all absolute test results to a common scale to order to increase our data sets. So for each age group, we calculated the relative difference between or compared to a reference group, most often the under 16, which then corresponds to 1. Each result was then weighted according to the sample size of the group. For lower body muscle strength, we see that both sexes do improve, especially during early adolescence, but boys have a much greater improvement. This is in large due to the greater increase in fat-free mass, which facilitates an increased muscle strength and power development. This is also explaining the similar pattern for both sprint performance. We see improvements during the years, as well as gym performance, but again, much greater in boys compared to girls. However, for intermittent endurance, which are tests that involve repeated bouts of high-intensity work with short recovery periods, the yearly improvement was actually quite similar between boys and girls. But as we can acknowledge, the sample size is really small among the girls, and this strongly limits the certainty of these findings. And generally, the results for girls from this study should be interpreted with caution. So, key takeaway, both boys and girls do improve, but boys improve more and for a longer period. There is large scarcity in data on girls, meaning these findings should be interpreted with caution. So, the next step was then to examine age and sex differences in physical characteristics from a cross-sectional perspective. For this study, we recruited 471 football and handball players in age groups under 14, under 16, and under 18. We tested football players from September to December, and the handball players from January through May, corresponding to their respective competitive season, or the latter part of their competitive season. This is also why we use the under age group categorization as the two cohorts recruited in different calendar years. This was also the initial testing for the longitudinal study. So this testing protocol we used for this one, we also used applied across all 3 testing points. And this testing battery consisted of anthropometrics, so we measured standing height, body mass, and seated height. These measures was also used to calculate maturation status using the Mirwald equation. And for a subgroup of our sample, the under 14 football players, we also performed a DEXA scan to measure body composition, and specifically fat-free mass. We performed a 30-meter sprint test, as well as a change of direction test, the OLT 40, which involves 4 180-degree turns. For strength and power, we performed a Kaiser leg press for lower body force and power, Nordic hamstring for eccentric hamstring strength, counter movement jump on a force plate, and an isometric hip abduction strength test. And on a separate day, we performed the yo-yo intermittent recovery test level 1 for intermittent endurance. So, looking at the results for height and body mass, we can see that in the under 14 age groups, boys and girls were almost identical in height, and girls even slightly heavier. But by under 18, boys were almost 9% taller and 15% heavier on average. And perhaps even more important is when looking at the individual variation. So within the boys under 14, there was as much as 40 centimeters difference between the shortest and the tallest, as well as for your body mass was up to 40 kilos difference. When we look at physical performance, here represented by the 30-meter sprint test, we can see that already at the under 14 age group, boys significantly outperformed girls. And between under 14 and under 16, we can see a large increase in this sex difference, which also coincides when boys hit their peak height velocity. But from under 16 or under 18, no further difference. The increase in sex difference from under 14 to under 16 was consistent across all tests. We see here for kind of movement jump, total force, and the yo-yo test. But between under 16 and under 18, the results varied. So for the 30-meter sprint test, we saw there was no further difference. For the yo-yo test, it even goes a bit down, while for total force, kind of movement jump, the sex difference increases. And here as well, we can see substantial individual variation. So for counter movement jump in the under 16 age group, you can see that there is a 20 centimeters difference between best and worst performance, which is quite a lot in this test. This large individual variation is likely partially explained by the relationship between maturation status and physical performance. So we found that there was a significant association between your maturation status and various physical performance measures, but the explained variance was much smaller in girls. So this suggests that maturation only accounts for a small portion of the difference in performance among girls, but the girls also had a more narrow maturation range, which gives the model less variation to explain. One reason that maturation may appear less strongly associated with performance in girls is that they gain less fat-free mass during adolescence. And we know fat-free mass is a major determinant of physical performance, and this is also reflected in the data. When we normalized lower body force and power to total body mass, we found there was a moderate effect size difference between boys and girls in the under 14 age group. But when we normalized fat-free mass, this was significantly reduced. And it indicates that fat-free mass is a primary driver of performance in lower body force and power, and is likely a far more appropriate basis for comparing boys and girls than total body mass. And also interestingly, when total lower body mass was normalized, total lower body force was normalized to body mass, we found no significant difference between the age groups among the girls, though it had a significant age group for total force. And this likely reflects that increases in strength may be largely matched by increases in body mass, and that girls have less increase in fat-free mass. So the key takeaway from paper 2 is that boys have significantly better in performance already at the under 14 age group, and that this difference increases substantially to the under 16 age group. We also see that for fat-free mass is a key determinant of sex difference in force and power in youth athletes, and performance is strongly linked to maturation status, but more so in boys compared to girls. Now, while cross-sectional studies comparisons help us understand differences between groups, they don't show us how individuals actually change as they grow across 2 years to track their development across age and sex, and also see how maturation influenced those changes. So our sample consisted of 248 players from the initially recruited sample, but now only the under 14s, under 16s, as there were too many dropouts among the under 18s. They were tested annually for 2 years, so resulting in 3 time points, and we used the same testing procedures all years. Between group differences was assessed using a mixed model analysis, and we included all participants who had a minimum of 2 timing points. And we also performed a multi-level linear regression to investigate the association between baseline maturation and change in performance from the first time point to the 3rd time point. So, similar to both paper 1 and paper 2, we see a similar pattern for growth. Boys grow more than girls, and this rate also reduces with age. And again, we can see a substantial individual variation. So using, again, boys under 14 as an example, some only grew 4 centimeters across a year, and others as much as 12. Some only gained 1 to 2 kilos, others 16. So moving on to physical performance. Here on the left, you have a table that indicates if a group significantly improved in the tests across a year or not. And what we see is that nearly all groups did significantly improve through the study, except the oldest girls. When we look at the between-group differences for average yearly change, we see that the boys under 14 improved significantly more than the under 16s at both years, as indicated by the green X, and they also developed significantly more than the girls in the second year. So overall, boys seem to experience greater development across 2 years, but there are yearly variations. And improvements were also larger among the younger age group. And across all groups, as we've seen so far, and also with the following tests, individual variation is considerable. It was especially evident in the under 14 group, where you can see some improved their performance by more than half a second, and others had even a large reduction or decline in performance across 1 year. When we look at total lower body force, we see a similar trend that almost all groups, again, except the oldest girls, did significantly improve the first year, though only under 16 boys improved their development also in the second year. And besides under 14s boys who improved significantly more than the under 16s and the girls in the first year, there's no difference between groups. When we again normalize to body mass, improvements nearly disappeared. This shows how absolute strength strongly depend on changes in body mass and potentially underlines the need for more targeted strength training to improve strength relative to size. Counter movement jump, we saw a clear sex difference across almost all age groups, but no difference between the age groups. And the limited improvements that we saw in girls may reflect a combination of a smaller increase in fat-free mass and a relatively greater increase in fat mass during adolescence, which increases body mass without contributing to force production. For the yo-yo test, only the under 14 boys experienced any significant development. For the association between baseline maturation and improvement in physical performance, we found significant association for the 30-meter sprint test, meaning that athletes with an earlier maturation status will likely improve more. But explained variance here as well is quite small, indicating that other factors as well play a substantial role in sprint development. For total force, we found no association, and for the counter movement jump, there was a significant relationship for the girls, with not only a smaller rate in development with higher baseline maturation, but the most mature players even showed a decline in performance. Lastly, an important finding from our studies was that there was a lack of significant improvement in eccentric hamstring strength when normalized to body mass. This we also observed in paper 2, with no significant difference between age groups, and we can also see a similar one for hip adduction strength. And hamstring and hip adduction or groin are two muscle groups that are highly susceptible to injury in sport, or especially in football. And it suggests that there is also a need for more specific strength training during adolescence to address these areas. So, key takeaway from paper 3, boys generally show greater improvement compared to girls, but the difference is not significant across all tests, and also yearly differences exist. Sprint was the only measure where development was linked to baseline maturation, but it has had small explained variance. As with any study, there are some limitations that may influence how confidently we interpret these findings. So first of all, there was an uneven sample, especially substantial loss of girls in that second year, among the oldest girls particularly, which reduces our statistical power and also limits detection of sex-related differences. Because fat-free mass plays such a major role in performance and difference between boys and girls, if you had a larger and more balanced sample, this could have provided a clearer understanding of fat-free mass contribution to development and performance across several age groups. Average maturation for the girls was almost 1 year past their peak height velocity, meaning they might have missed their period of greatest performance gains. And lastly, the maturity estimation, or the method used, has some known validity issues, including a lower accuracy for early and late maturing boys, as well as a tendency to underestimate maturity in girls, meaning some athletes may have been misclassified. With these limitations in mind, we can now turn to the main conclusions of the project. So, both boys and girls seem to improve during this time, but boys improve more and for longer when we compare by chronological age. And this is largely due to a greater increase in fat mass and more growth. In both sexes, the greatest gains occur in early adolescence, although the rate of development varies across time points and also across different physical characteristics. And we found a significant relationship between maturation and physical performance, but smaller in girls. And while some association was found between baseline maturation and performance development, this was also quite small. So, bringing all this together, what can we actually use these findings for in a practical application? Since girls mature earlier, gain more fat mass, and show limited progression in several performance measures, they could likely benefit from earlier introduction to strength training, which may provide a boost in their physical performance development. As we found no significant development of hamstring and hip adduction strength when normalized to body mass, this may suggest there is a need for also more injury prevention training already from early adolescence. And large variation in both growth and performance development and performance in general highlights the importance of individualizing training. Early physical advantages often level out throughout adolescence, underscoring the need for patience and long-term development. Thank you.
Thank you, Lars Martin, for an excellent presentation of your PhD. We are looking forward for a scientific discussion between you and your opponents. And we start with the first opponent from UK. The word is yours, John Oliver.
Sorry about that. You can all hear me now. So thank you very much. Thank you, Lars. Another excellent presentation. So well done on that. More importantly, well done for being here today, presenting to everyone on your thesis. It's a really big, difficult task to produce a PhD thesis, and many people don't make it to this stage. So well done. Congratulations also on the content of the thesis. It was really nice to be able to read it and see your research. It was really well written, showing some good knowledge of the other literature out there. We had a real mix of research designs across your papers and studies, which was nice to see, and a range of statistical approaches as well. And also some really nice visual presentation of your results, which I think really helped the reader to understand the data. So thank you for taking the care over your thesis. It was a nice read. I was hoping I could start just to get a little bit more of context and background from you. So why did you choose do this thesis, this research, and there's lots of things that you could research. So what was the motivation for you behind your research topic?
I think first of all, it was timing. So it's not long after I delivered my master's, this was available as an option. And having been in football and working as a strength and conditioning coach from past 2 years at that moment in a female team or a girls team, where age range ranged from I think like 15 to 30. I had some interest from then on like the earlier age stages and how training affects them compared to like the mid group and also the older athletes. So when this project came available, pretty much, the theme of it seemed really interesting and I think very valuable, because young athletes are our future athletes pretty much, so getting more knowledge on how we can help them on their way to the senior level was really interesting at that time.
And then, just what were some of the challenges you really had to face over your journey?
Yeah, I think that started already when we tried to recruit the athletes or the teams. So we wanted quite a large sample. So that meant we also had to get several teams, like preferably we would have gotten like larger teams, so we didn't have to have so many testing sessions. But some teams, there were like 6 players that was interested. Others we did have actually around 20. But the recruitment process there was challenging. We had to reach out to, can't remember how many teams, but all over the city, calling, emailing, messaging, calling again. So the whole recruitment process in the beginning was challenging. Then we had to do it all over again for the handball group. And also just getting them back to the testing for the follow-ups the next year was not that easy always. I remember specifically one team. We started early in the fall, around August, September, trying to find a suitable date and just postpone because there was never a time that fitted. So we tried just before Christmas, but then it couldn't after all. I think we ended up in mid-January before we can even get some from that team coming back for testing.
But it's a good advert that a PhD is much about perseverance and determination
Sure.
and sticking with it as much as anything else. So well done. When you were starting out your PhD, or in the early stages, I just wondered if there were 1 or 2 really key papers that shaped what you were doing. Obviously, you reviewed an awful lot in your systematic review, but were there 1 or 2 papers that really stood out?
Oh, that's a good question. It's a long time now, so I can't. I know there was like a few that I used a lot. I think I can't remember all of them. One that I do remember is the one by, I think it's Wrigley, 2014, looking at the longitudinal development between football players and non-football players, and how the developments differed so much actually in that paper in physical performance compared to the non-athletes. So that was partly one of them. I think also the Landgraf study that also showed in the trial lecture. They looked at longitudinal development in UMax, and they found that there was no difference between group, then looking at like how various physical performance characteristics differ so much in how they develop during that time. I think that's at least.
So 2 nice studies, and I think you picked out 2 longitudinal studies then, and even since the Wrigley study in 2014, we probably don't have a lot of longitudinal research studies. So definitely still a gap there that you're able to address with some of your work. And yeah, agree. Those studies show some interesting findings about the value of young athletes doing a lot of training. Do they gain more than just the general population, etc. In terms of your first paper and your systematic review, you know, that was really comprehensive. I think I've noted it correctly that you had 176 studies in there. So, you know, definitely looking over a large volume of literature, which I'm sure was quite demanding to synthesize. Once you'd gone all through your review, and I was interested in how that shaped the later work, why did you think it was important to have a sex comparison in your research versus, say, maybe just focusing on girls in the empirical work?
Well, not mostly, but I think like large reason that was important to have the sex comparison is, well, first of all, it was done so little literature on girls. So we know that like most of training recommendations and that kind of stuff is usually from studies on boys. We just translate to girls to actually see then how the development differs between them. That was important and necessary to better understand the trajectories and development patterns. I think that was like the main aim of it.
There could be a counter argument in your review. You show that there's lots of data on boys already. So should all of us now as researchers just really be focusing on young female athletes?
Fair point. I think like the point that I also mentioned in that paper is that there's a few studies that actually compare them in the same, using the same also the tests. So we may compare like between papers, but then the papers might use total different measures or ways of testing them. So looking at the sex comparison using the exact same testing battery to actually see across equal tests how really different they do develop.
And I know you articulate some of this in your thesis, but in your presentation, you rightly pointed to the effects of maturity on development. So what was your thinking then in the thesis to, after review, take the approach where you decided to focus on age group categories, even though that, you know, there's a lot of difference in maturity within those age groups?
I think for particularly both first and the second and the third paper, a lot of it was down to getting more knowledge at how we measured maturation, how limited it is on certain aspects of maturation in these kind of groups, and maybe particularly among the girls. So in retrospect, I think like the maturation aspect is likely the most interesting part of it, but I didn't want to put too much emphasis on it when our estimations for maturation was, the precision of it wasn't that good. So if we maybe had a better precision or a better estimation, or even more data on the actual skeletal age that we started measuring for a group and never actually came out to analyze, that I think if we had that from the get-go, then I think the emphasis would have been more on the maturation aspects.
So your review highlighted that, you know, I think of the 176 studies, you maybe had close to 30 that had measured maturity in some way from memory. And then across those 30, they'd use different measures of maturation. So there wasn't consensus. I wondered what your thoughts are then moving forward as how we all approach measurement and research with this sample of youth athletes. Should we all now be using a single measure for maturity so we could compare across studies moving forward? And if we did, what would that measure of maturity be?
Oh, that's a good question. I mean, it would streamline at least the results if you all used the same way to measure, but then also that measure has to have the correct precision to actually know that what we find can translate to true reality. So what would be the best measure? I mean, like, using DEXA scans or X-rays on the hand is likely the gold standard and what gives you the most precise estimation. But it's difficult to get a large sample from that. There's a lot of work and there's a lot of logistics and financial in that. I think maybe the Camis Roche is one of the more precise estimations, at least from what I've gotten to know. So if I've done it again, I'll probably try and use that one.
So, I mean, DEXA would be our gold standard measure, and if we could all use it, it would be great. And you know, even getting to use it in our research and at laboratories is difficult. So, certainly very difficult to apply in the field. You mentioned the Camis-Roche method there, which is a sort of non-invasive measure of somatic maturation. So you can get from measures of height, etc. You went down the road of choosing the Meerwald equation, and I've used both of these approaches. I just wondered what was your thinking for choosing the Meerwald estimation versus Camis-Roche or anything else?
I think it just leads down to limited knowledge at that point. Not getting too much, or not going too in depth on what is actually the best message to use. I think I read several papers that used the Meerwald, and at that point thought that was a decent idea. Before later in the project realizing could have gone another way. But yeah, I think like at the time that we decided that one is the one we're going to use, didn't really know better.
Because you pointed out some of the limitations of the Meerwald approach, which we could see. What were some of the advantages of using it, though? What were some of the positive reasons for taking that approach?
Well, the positive is it's easy. So like compared to the Camis-Roche, when we needed parent's height, so getting additional information from a cohort was already difficult to get them to do anything, really. So I guess that's one of the answers. And yeah, as we measured like standing height and growth or body mass, adding the sitting height was not a lot of extra work. So it was usually just feasibility of it. It was easy.
Yeah, I'd agree, and that's certainly why I've used it in some of my own work. With some populations, getting parental height can be a little bit difficult with the Camis-Roche, and the two of those methods both have their positives and negatives. And I think for the Meerwald approach, it's more reliable the closer you are to peak height velocity. And you do get to identify peak height velocity, which you don't necessarily get with the same accuracy with the Camis-Roche, and arguably being able to identify the period of peak height velocity is quite important. Yeah. You know, some of the things you mentioned in your trial lecture around injury rates maybe being higher during that period, etc. So it's useful. So it certainly has its limitations, but also has its uses as well. So I think it's nice to sell the positives as well.
That's true.
Other things from your first paper and your review work, you noted that training load had an influence on the response. Perhaps not surprising. How did you then take that forward into your empirical work?
Well, at the time that we were writing the systematic review, we were also trying to collect training load data. So using both GPS measures for some of the football teams of all the age groups, and as well as having all the athletes reporting RPE every second week, or for certain periods throughout the year. So we were planning to use that kind of data in our analysis on development to see if it had any association between them. The problem was that getting good quality data seemed to be too challenging. So GPS was fairly good, but I'm not sure if the data could have been actually used for that, that kind of measure. And the RPE data was, I think at some point we had 25% response rate. So what we got from that was too limited to actually be able to use it. So that's probably the reason why we didn't end up actually analyzing it in a better degree.
So definitely part of the challenges again, and the perseverance. I think monitoring load is difficult even in a professional club, professional academies, where there's a lot of staff, and difficult to get any athletes enthused about giving their perceived exertion scores or trying to do that. I just wondered what approaches you took to trying to maybe get that data. Was it a case of it was reliant on the coaches really trying to get the children to fill it in, and was it them filling it in on paper, or did they have to go on an app and use some technology to record their load?
So we tried various measures. So additionally to the training load variables, we also tried to collect injury data using the OSTRC questionnaire through the athlete monitoring application, which had similar trend that we started off fairly good, but after a year the response rate was just too poor. But in both cases, so we tried various methods. So they got a notification on the day that we had set for them to report. So the injury reporting was every other week, and the RPE was not that often. Then I got another notification the other day, in 2 days, and for third day for the injury prevention, and second day I think for the RPE we sent out individual messages. That was quite a lot of work in periods. We also tried to involve the coaches, so we moved the reporting to the last session of the week for each team, and then trying to remind the coach to help us remind the kids to do it. That also didn't work, because whenever we sent a message to the coach, they forgot about it when the training started. So that was actually quite a lot of work for no additional gains. That was very nice.
It's difficult when you realize your priorities aren't the same as other people's priorities.
Yeah, I don't know. So the next I think after time we just gave up, because like the ideal here would be actually being present when they were doing it. But I think we had 16 teams or so involved, so the logistics around that was just not possible. So maybe we should have gone with a smaller cohort and a group that we were actually able to follow up more in person, or getting the coaches more invested and involved somehow. But yeah, it was
something you can try and design into future studies.
Yeah, for sure.
And just one final question related to the review work and moving into the empirical work. When you did the empirical work, did you find any results that were particularly surprising compared to what you'd found in your systematic review?
I think, especially in the paper 2, from between the under 16 and under 18 age group, where we probably would have expected a similar trend that we saw from under 14 to under 16, that the sex difference across pretty much all physical measures increased. I would have kind of expected that between under 16 and under 18 as well. But what we did so, as I also presented, was that this varied a lot more. And probably part of it is due to just sampling bias when you're doing cross-sectional work. But it could also be that the oldest age group, oldest girls, were exposed to more strength training. So we had a small data set where we looked at the training volume, and they did at least report a higher volume of strength training compared to the younger teams. So that could have been part of it. But I think like the combination probably of that and just sampling bias is much of the reason that we did not probably find that expected.
And then you've done a lot of background work, a lot of review work, and then you ran your own empirical studies. So nice to see multi-site and large sample sizes. I think you've already articulated some of the challenges and difficulties with that, but it was definitely nice to see within those papers. We've also already touched on maturity, so just wanted to go into that a little bit more on paper 2. You then decided to group your participants into maturity groups, but you also acknowledge there's some error in the maturity estimation. So how much risk was there that you might have misclassified what group an individual should sit within?
How much? Hard to say. Just based on sex, I would guess overall it would be higher, or it would be greater among the girls. For girls and boys, we categorized into the pre-group, mid-group, post, and post-1 to actually get more of a spread. And I guess, as you also mentioned, that its most precision, or the greatest precision, is around the peak, the mid period. So probably the further you get from that, then particularly maybe the post-1 group for the boys would have the smallest precision, and for girls as well, the overall precision is quite low. And again, we also didn't have the pre-group for the girls, so we also missed that group, but yeah, no limitations. It might have been some of the girls that actually was in the pre-group, and that could have influenced how we also reported our results.
Because you had, you reported in your methods that the Meerwald equation, when it's estimating years from peak height velocity, it's got an error of approximately half a year, about 6 months. And then you tried to get quite a lot of maturity groups. I think as you explained there, there's 4 of them from memory: pre, mid, post-1, post-2. That meant some of those groups were quite narrow in how long they expanded. So, for example, you have your post-1 goes from half a year peak height velocity to 1.5 years.
Yeah.
So the window is 1 year, but anybody you place in that window, we know there might be half a year's worth of error in their estimation. So would they move out of that window? And with that knowledge, if you were trying to be very cautious, are there any other ways you could have designed the groups to try and mitigate some of that risk of misclassification?
Probably could have used just a broader group. So either instead of 1 year, then use 1.5 year or even 2 years. I guess then we would have ended up with about 2 groups per sex. And of course, we wouldn't get like the nuanced findings from it, but probably more precise results, I guess, compared to that.
Yeah, so I agree. Wider groups would certainly mitigate some of that risk, bigger time intervals. And if it was 2 groups, maybe you'd have pre and post peak height velocity. That's actually how Meerwald recommended the equation of should be used, but lots of people use it slightly differently, and I certainly have myself as well. The other thing you could have considered that some researchers do is to actually put some gaps between your intervals. It means you lose a bit of data. But if your circa group was minus half a year to plus half a year, you could then have a gap of 6 months and then start your next interval. So it does give a bit of data loss, but it gives you a bit of a buffer between groups. So just something to think about moving forward.
Oh, yeah.
Also on this theme of maturity, and you touched on this very much in your presentation, is that within age groups, there can be quite a profound effect of someone being an early or a late maturer. And I think your figure on skeletal age at the start of the presentation showed that biological age and the same chronological age might differ by up to 5 or 6 years. So quite profound indeed. I just wondered whether you considered running any sort of analysis on early versus late maturers, either within age groups or across whole samples, to see how much of an effect that had in boys and girls and whether it was different.
For paper 2, I think like at some point I actually did that analysis. I at least remember having some tables for it and looking at the difference between them. Exactly why we didn't include it. Likely we just had already a lot of data, so we felt probably that it wasn't sure if it's added anything. It's interesting analysis. Can't exactly remember the results, but I remember that there was some difference between the pre and mid group, particularly in boys. For girls, we didn't have the range within a given age group. I think we mainly looked at the under 14 group and tried to see that within that group if the maturation categorization within one age group had an effect. I believe there was some difference. I didn't do any statistical analysis, only percentage difference, and can't remember that for some tests there was substantial difference between them.
Yeah, and there was certainly discussion of it, and I think this discussion was around the under 14s as a nice group to select, because particularly for the boys, it's around that peak height velocity on average, and therefore you might get a lot of variability with those who are early and late. And visually, you can see it in the figures where they're color-coded data points relative to maturity. So I could certainly get a sense of maturity effects. If you did want to classify someone as being late or early maturing within a given age group, how would you go about doing that?
Fair point. I mean, likely using the same intervals as we did for the whole sample, but just specifying for just one individual group. So if you have large enough group, you likely also have enough variation that you can use the similar categorization in that age group. So particularly the younger age groups that we saw in the presentation, where biological age tend to vary the most. If the group is large enough, I guess you can be able to actually use those similar intervals.
Yeah, and normally you'd use a Z-score. So if someone is 1 Z-score away from the population average, they're early or late, or maybe you take it down to half a Z-score. That's used quite a lot. I just wondered if you knew, just from looking at the data, what the range would be within one of the age groups. So, you showed some of that range in maybe someone improving their jump height by 20 centimeters or body mass by X amount, that it was quite large. What did the range look like in terms of maturity within a group?
Good question. The range, I can't remember. I know the standard deviation was about half a year or so, plus minus. So I guess then total range would at least be above 1 year. Or yeah, but no, I can't remember exact.
It's just interesting to know how much your sample reflect the general population, where that range might be 4 or 5 years, range in biological age within a chronological age group, or actually in your sample have a more homogeneous group being selected into the sport. Has the sport chosen to select those who are more early maturing, for example, so you're getting a bit more of a narrowing down in your sample. In paper 2, you present some regressions as well that just show the sort of developmental trajectory with advancing maturation. How do you think those could be used in practice to help coaches, those working with youth?
I guess it could be beneficial in relation to classifying talent selection, probably, to see that if you have athletes that are early or late mature, this is how likely their physical performance would be at that time. And then you also can have a bit better understanding that, okay, this athlete who doesn't have the best physical performance in this group may achieve that in just a few years, a similar one. So being aware of it when it comes to talent identification, where often the early matures are selected in front of the late matures just due to the physical performance at a given time, it could help at least worrying a bit out the difference there, and maybe help the late matures not falling that long behind.
So if we had 2 athletes who were in the same age group and you had their fitness scores and it was a bit of talent ID, talent selection going on, but you knew they were different maturity status, would it be possible to do some sort of correction or prediction where you predict both of their scores whether they're at the same maturity status?
Ooh, that's a good question. I guess it is possible somehow. Again, it is difficult to exactly predict how much they are going to develop, or just due to actually what their genetics and actual potential is. So I'm not really sure how much you can get for that. You will have some idea that the later mature will most likely gain more in the coming years, but to know exactly how much, I think it's difficult and depends on probably too many other influencing factors. So I guess the easiest in talent identification, not easiest, it's not easy at all, but probably the best is looking more at the actual sporting skills or the tactical, technical abilities at a given time, which is also what's most likely going to get them to the highest level.
I mean, I agree how accurately we could make those predictions is a little bit of a question. I just wonder, did you consider though that with your regressions, if you'd have reported your beta coefficients, that is the gradient of the slope, that would allow someone to make those predictions, and you could also calculate the typical error of estimate, the error in those regression equations and predictions, because some of them look like they'd probably be quite strong and some of them look like they'd probably have quite a bit of error. It changes between physical quality looking at your results. In paper 2, you also did quite a bit of work around scaling and thinking about body mass, which really important when we're working with any athletes who are of differing body size. particularly important with children because those differences in body size can be so large across age groups, across maturity. So nice to see. So you had some what we call ratio scaling, the just dividing by body mass. You had consideration of fat-free mass, which we saw in your presentation, and also allometric scaling as well. I just wondered if you could just briefly explain to the benefit of those in the audience of what allometric scaling is and why we might choose to use it with data from youth.
So the idea of allometric scaling is based on mostly older athletes, and that body mass is not there is not a linear relationship, specifically with strength and increase in body mass. So it's trying to trying to better see what also other factors are influencing here. Can't remember the exact definition of it, but that was the idea to try and show that the just growth is not the only factor influencing here, and that there are also several other that we can't measure directly with growth that will influence our performance development and also strength measured. But what we found was when we did the sample-derived exponents, there was actually, I think this was at 1 for body mass and total force, which then actually indicates that the relationship between them is quite strong, at least during this time. So we can then see that probably compared to an adult population, within adolescence period, there are probably more linked, at least in some phases.
And sorry, that was a bit of a cruel question because explaining allometric scaling is not easy, but it's nice to push as an examiner. And you're right, where you see the exponents coming out at 1.0, as you did for some of yours, it means they're equivalent to ratio scaling. Allometric scaling is really just considering the proportionality between size and performance, i.e. when we double size, we might not make someone twice as strong. Each time we double their size, the relationship might be slightly different. Across the methods you used and methods that are out there, what do you think would be your optimum way to account for differences in body size and composition?
I think at this point, the allometric scaling and the sample-derived are interesting, but I'm not sure if the evidence is quite there to actually use it confidently. So I think overall, it's easiest and probably also most understandable for most practitioners out there to use normal ratio scaling. And we'll give you a fair results anyway, an indication of how it affects it.
Yeah, I'd agree that the ratio scaling is certainly a lot more intuitive and has meaning for coaches, without a doubt. Fat-free mass was also useful because as a practitioner, it might be useful to know as someone put on muscle mass or fat mass, and as you articulated, that can drive a lot of the changes in physical performance. Do you think there would be any benefit of scaling using both fat-free mass and allometric exponents, i.e. allometrically scaling with fat-free mass?
Haven't thought about it, but again, I think it would probably give even more nuanced knowledge on how mass or various types of mass, and in particular fat-free mass, do affect the physical performance of certain variables, but not sure what quite the outcome would have been.
it's probably the same, probably in theory very good, and in practice a bit difficult for those working directly with athletes to use. But I think certainly in theory could be good for researchers. And just a couple of bits now, just feeding on from when you moved from paper 2 into paper 3. So you noted some of the benefits of allometric scaling, and again you showed them in your presentation when comparing ratio scaling to allometric scaling. You then chose not to carry on allometric scaling into paper 3 in the longitudinal study, so I just wondered why that was.
I think for paper 2, I found it as an interesting added analysis, and I didn't use it for paper 3. No good reason, actually, other than had other aims in mind, and was more important for us with just the longitudinal development and not so the more nuanced analysis of it. So for paper 2, just the cross-sectional study, which isn't that novel by itself, we tried to find some added analysis to try and just increase the novelty. But for paper 3 could have been an interesting added analysis, but
Yeah, I mean, I just wondered, and you did pick up fat-free mass again in study 3, which was nice to see and useful. And I think the allometric scaling is relevant all the time, but it's more relevant in a cross-sectional design where you go longitudinal and within subject, it's maybe not as relevant, particularly over reasonably short time periods. You also reported in an appendix to paper 2 the training volume. And that was quite interesting to see. So as difficult as it might have been to get all the training data, actually just having training hours is quite informative. So your boys were training around 14 hours a week and the girls 11 hours a week, which seems like they're exposed to a reasonable amount of training. Were those the same participants who were in paper 2 who became part of paper 3? So could we assume participants in paper 3 were exposed to a similar amount of training volume?
It was from the same sample, but I didn't look specifically into if those that we had sound training load or training volume data on was the ones that were also included in paper 3, since we did lose a lot of players over several reasons. But I would assume that at least for baseline it would be similar, and that's also likely, that's hard to say, but it was from the same sample that it was. But that was from as I talked about the injury reporting that we did first year, that the response rate dropped so much that this was just from one condensed period from those training in the first year of the study.
This question can go across the data in both papers 2 and 3. For the amount of development you saw over time, whether cross-sectionally or longitudinally, for the amount of training exposure there was, quite a lot of hours per week, do you think that training was really aiding or accelerating physical development? I mean, you didn't have a control group, so it's a bit of a tricky question, but were you able to compare to data from the general population, for example?
For paper 2 and 3, we did not. But if we use the training volume that we found in paper 2, or at least try and evaluate it for the results we found in paper 3, and that the older age groups, can't remember exactly between the under 14 and under 16, but did see the older age groups did have more strength training hours on a weekly basis. And as we noted in our longitudinal results, that the under 16s actually improved as much as the under 14s for both kind of movement jump and total force, at least for part of the study. This could have been due to them having a larger volume of resistance training, whereas the younger boys develop solely, or not solely, but mostly just due to their boost in biological development.
Yeah, and I would guess I was really just wondering of whether you were able to look at any data in the published literature that would have just been on a general population for, some fairly popular tests like counter movement, jump heights, just make a bit of a judgment of, does your sample look like they were developing more than if they were just reasonably active rather than doing a high training volume?
So I did that in paper 1, so I actually did have some papers that from the general population that had looked at it. So in retrospect, I guess it would have been interesting to actually use those also in paper 2 and 3 and see how they corresponded. So why I didn't do that, I can't really have a good answer for. But yeah, and I remember from the systematic review when we did just at least small analysis of it, there was no clear trend that the team sport athletes did develop more than the non-athletes. And there was some difference also just between the tests. So in some tests, the general population improved more and team sport athletes improved more in other sources, and any clear indication, at least from that the added training activity from doing team sports added added anything.
And you also already touched on that there was quite a dropout throughout paper 3, particularly into the final time point. You just give a bit of insight to why that was. Was that dropout from participants just withdrawing from the study, or were they dropping out of sport completely, or moving to different sports?
Yeah, so several reasons. I think most, at least for the older age groups, it was that they dropped out of sport, started studying, those kind of things. Some just changed clubs, or found another team. So we tried and get those back in, but it was difficult. And some also dropped out due to not want to participate anymore. So what kind of range in the reasons why they did drop out?
And then when you go into those low sample sizes by the 3rd time point, what effect does that have on your ability to detect significance and draw the correct conclusions?
I think for the boys, it was overall fairly good, because we had at least a decent sample size. For the girls, in the first year, I think our results are quite reliable, but in the second year, and then especially looking at the age group difference from within the girls, where the sample sizes was, I think it was around 25 for the youngest girls and 7 for the under 16s. So for the oldest girls, I think the results, at least if you look at the already individual variation within the group, having only so few, will definitely reduce the statistical power when we look at that group.
Yeah, thanks. And there was one bit or a couple of areas where I struggled a little bit with just reading through the results in paper 3, where I couldn't get agreement between the results you'd written in text and what were in the tables. And I don't know if that was just my interpretation, or if there's just a few errors in there. So, for example, in text, you write about the changes in performance comparing, say, under 14s and under 16s. And the change values you give in text don't seem to correspond quite to the change values that I get when I look at the mean values in the table. So as a couple of examples, for the under 16 boys, you would say their 10-meter sprint time reduced by 7/100ths of a second. But when I look at the data, it's the mean values in the table, it's going from 1.91 to 1.82. So it's 900ths of a second. And then similar for 30-meter sprint time, there's a bit of a disagreement. Was I reading something incorrectly there, or is there just some errors in what's being reported?
I mean, of course, it can have been an error in how I reported it. I think it's also likely just due to how, from the table, that's absolute result for all groups, while the change score is an estimate from the statistical model or the mixed model. So it's more like an estimate of each individual change compared to then the average group results in the table. So I guess there is some statistical explanation for it that I can't really go deep into.
I don't know, it's good to have that, that hadn't crossed my mind. So yeah, it's a good one to point out. I was then just wondered if you did anything to clean the data, whether you ever thought there might be some spurious results or outliers. So I guess a couple of examples: change in height. A few of the girls got shorter as they got older. Not by very much, but does that mean those are non-valid results, or is that maybe just within the measurement error? And then some of the growth rates, and actually I think you might have taken the outliers out from your presentation at the start compared to the thesis, but there was some, I think a boy and a girl who had a growth rate in stature of over 20 centimeters a year. So yeah, just did you do anything around what might be spurious results or outliers?
So there were a few of those. So for the ones that got shorter through a year, that was most likely just measurement errors. It was only at least, wasn't many centimeters, but yeah, it was likely just due to that. The specific one that you mentioned that grew 20 centimeters, that was just an error in the data set. And if I remember correctly, that was 2 athletes where the second year it was the wrong ID. So it was wrongly ID'd for that specific person in the second year, which I didn't caught before actually doing making a presentation for this one.
Yeah, well, it was good to see the correction in the presentation, and it's a danger of having good visuals is the outliers get spotted.
That's true.
Easily.
Yeah.
You also showed that analysis around baseline maturity, years from peak height velocity, and then just physical development. But that was based on the visuals, and the statistical analysis used linear regression. And I wanted to know whether you thought linear regression was the appropriate type of modelling, i.e. would you expect changes in performance with advancing maturity to be linear or non-linear in nature?
Yeah, that's a good question. I wasn't really quite sure how I was going to do that exact analysis. So it was mostly based on my current knowledge at that time of what I thought was maybe not the best idea, but one way to try and look at the association between them. So pretty much comes down to that. If it was the best idea, probably not. And as you say, they are probably not a linear relationship, and it will be, also as we saw in the results, there are yearly variations, and it's more fluctuating than it appears in that kind of analysis.
And you showed it in your opening presentation. You had the growth curves on average for boys and girls, and then lots of them together from that Portuguese data. So you can see rates of change, whether it's height or weight or speed or strength. That it's not non-linear. It's non-linear when it's over a large period of time. If you go into a shorter window, maybe it begins to look a bit more linear. But I just wondered whether you were surprised at all about the spread of the data and how it looks. So particularly for the growth type data, height and weight, they look like they've got the highest values in the year or two before peak height velocity, whereas by definition, peak height velocity would suggest that, certainly for stature, your biggest rate of change should occur there, but your results and visually actually in your population, it looks like it was occurring 1 to 2 years before peak height velocity.
Fair point. I can't really visualize the figure right now, but yeah, that is unexpected, and I don't think I actually noticed it. But I remember that we did a similar analysis for like peak height velocity measure and height, not related to that exact analysis. And then at least we saw the greatest height growth around peak height velocity. But why it didn't show that in this specific analysis, I'm not sure, and I actually didn't notice.
Yeah, just be worth having a look at figure 13 in your cap, and I'd have to check where it reappears in paper 3. But it's you get a strong linear relationship between the change in height in years at peak height velocity. It's a strong linear negative relationship, which means showing your growth rates are highest before peak height velocity and then steadily go downwards, which isn't really what you'd expect. But
well, as you
it might be something to do with, sorry, you go.
Well, as you point out, the expected results is likely that the largest growth rate is around peak height velocity. So it could just be due to like the large variation that we had in the group, but also perhaps the precision of the maturity assessment. But yeah, no, it's of course reasonable to think that around peak height velocity, as it is peak height velocity, you would expect to have the largest growth.
And then I guess just finally to round off on the practical applications of all of this work. So what would coaches know, or could coaches do differently now from this body of work? What could you tell them that you've shown through your review work and your empirical work to inform how we should maybe look at the development of girls and boys, and how that might give us some thoughts towards what we do with training?
I think one would be to practice more patience. So considering the talent out of identification, or not problem, but the challenges around it, that we see at least some tendencies in this one that also confirms previous results that early matures do have greater performance, and also that later matures most likely will gain greater development gains over a few years. I think that's one, to just have patience with our more late mature athletes. Another one would be, like also pointed out both in the papers and presentation, probably particular for the girls, that with their overall less improvement or development during this time, I think it would be valuable to introduce them to strength and conditioning training at an early point to maybe try and boost this performance development throughout this time. And of course, there are challenges around implementing this with resources and actually having qualified supervision to implement these programs, but I think that would be really valuable. Then also, I think over the whole group, relating to like the lack of improvements in especially hamstring and hip adduction muscles when they are normalized to body mass. So getting also into more injury prevention specific training at an early age could help us improve these muscle groups and also prepare them better for the demands that are coming and the common injury types that we see in team sports.
And I think that's sound advice. Thinking about that advice within your population, just coming back to the training load that was reported, that seemed like they had a reasonably high training load. The things you're advising, do you think the athletes need to do more training on top of what they're already doing, or do you think they need to do different types of training and change some of what they're doing?
Yeah, I don't think increasing the overall load is the best option, but I do believe that probably improving quality of the work and more intent with what we actually do, and not just throw in some strength exercises and believe that I will solve everything, but have it probably, at least from some ages, more structured and do it consistently. I think one problem is that, although picked up in the trial lecture, that a lot of teams do like more short efforts where they put in strength training and do that for a few weeks and then nothing for the rest of the year. And so from the training volume that we added, it might have been that this is a period where they have additional strength training, but if you look at another part of the season, they do close to nothing. So I think more the consistency of the training is probably one of the greater issues. I at least experienced that myself, that teams are very good for a short period, put in the work, have some strength sessions for the team, but they do so for like 6-7 weeks, and then the rest of the year they don't do anything. So they get a small boost for short period, but from the long term that won't really do anything.
Yeah, well, it's a nice combination of own experience and observations, and actually the empirical evidence as well coming in. I think that's a nice place for me to finish. I've enjoyed our discussions. It's been insightful, and I'll pass on to my colleague now.
Thank you, Professor Oliver, for very clever questions and good answers from the candidate. Now we will take a short break, 10 minutes, and we will be back here in 10 minutes for the second opponent. Thank you.
Ska jag öppna? Så blir den grund.
Ja.
Så där den.
Okay. Ja.
Så.
Welcome back. We are looking forward to the discussion between the second opponent and the candidate. The floor is yours.
Thank you. And thank you to the Norwegian School of Sports Science for inviting me to serve as second opponent. And congratulations to you, Lars Martin, on an impressive body of work, an excellent trial lecture, and a solid defense and discussion with the first opponent. So, as a second opponent, I will mainly focus on the methods you have used. So, you have done an impressive data collection, you and your team. You have a large sample size, a large selection of physical tests, 8 tests, and if my calculations are correct, you and your team have done at least 4,514 physical performance tests. And I guess some of them, or I guess it's more, because some of the tests are deleted from your thesis. So it's really impressive. And I've done cross-sectional and longitudinal studies myself, and I know there's a lot of challenges. So my first question is, how did you experience the data collection?
Let's see. I mean,
It's a wide question.
yeah. No, I mean, in the beginning, at least when we got into it, it was quite exciting, fun. I mean, like doing your tests, it's when you find a flow, it's quite nice. When you do it for 2.5 years across whole fall and whole of spring, then you get a bit tired of it.
I can see that.
So like that's just doing the actual test and the and on the day, and then you also have like all the logistics and actually getting teams back and trying to get as many as you can back for the next year. That was also quite a challenge. Used several months to actually find a date. Came to the date, couldn't make it. Had to find another one, and that's how it went on for 2.5 years.
Yeah, I've experienced the same.
And that's like the physical testing part, and then as it was briefly mentioned previously, the questionnaires and the training load data. So it was a quite logistical challenge at times, especially when we had simultaneous physical testing and the GPS monitoring. So we may have like 3 or 4 days of testing within a given week, and we also had maybe 1 or 2 teams where we had to be at every training session for 2 weeks. So there have been quite a lot of people involved in this, and wouldn't have been able to do it without everyone contributing. So we had, I think, sometimes I had 2 master students and 3, 4 research assistants just helping out with all the data collection.
Yeah. And my next question is then, which of the tests were you most involved in? Because you have 8 different physical performance tests.
So how the test day was structured, we can go into that. We always did the anthropometrics first. So we did height, body mass, and seated height with the whole group before going into the gym, performing the warm-up. Then again, with the whole group, we performed the 30-minute sprint test and a change of direction test before we split them up. So then it was based on how many there were, either 2 or 3 groups.
So you follow them from the start
Yeah.
and to the warm-up?
Yeah.
Yeah.
And depending on who was helping me with that time either did the anthropometrics or was helping them with the questionnaires that we did simultaneously at that time point, and then doing the warm-up, or someone helping me did a warm-up, and then a sprint test, and then a change of direction test. Then we split them up in 2 or 3 groups. So then if it was 3 groups, then it was Kaiser leg press alone. It was a Nordic hamstring kind of movement jump together. And then it was the hip adduction and the shoulder rotation test. Those used the same equipment in other groups. So then 3 groups and 1 testing personnel at each of them. So usually, if it was then 3 people, I would cover 1 of the tests, and usually the one where the other didn't have that much experience. So I was involved in all the tests throughout the project at
That's
various amounts.
Yeah,
And,
that's impressive.
when we were lucky enough to actually have maybe 4 people, so 3, including me, then I had more like overview and responsibility than going around helping.
Yeah. But why did you choose the selected physical tests?
It was
Is it a-
mostly actually based on similar testing batteries that is used in football. So especially in Norwegian top level of women's football, they have every start of season and the season the option for this testing battery through. I'm not sure what it is in English, but Idretten Selvsenter. So they offer this to all the teams, and that is quite similar testing battery, except for the intermittent endurance and the shoulder rotation. But we included the shoulder rotation. In the beginning, we thought it could be interesting to look at how that developed in handball players compared to football players, and then similar with the hamstring and hip the other way. So yeah, the testing battery was largely based on that. So then at least we had an option if we wanted to compare that to senior level in both male and female, because I also use similar tests for senior male football players.
Yeah, and it's based on physical tests for football players. But you also included handball players.
Yeah.
So how many football and how many handball players did you include?
Oh, that's a good question. I can't remember in total. I remember there was some differences between the age groups.
But was it a reason why you also included handball players?
The reason was mainly to look at more of team sport in general and not specifically for football, as handball have been done less research on handball players. That's why we want to include them as well, and then get a better overview of typical team sports and how to develop. And then we also would have the option to analyze between sport differences if we had large enough samples.
But you didn't.
We didn't.
No. But did you expect handball and football players to perform similar on the physical tests, or?
If we consider the just general biological development and what we see in non-athletes that do develop consistently even without training, I think that would explain that we would expect similar improvements. I think there could be differences just due to, at least in the older groups, that football players are more often have some experience with the tests because it is more common. They are usually more resources and greater possibilities for actually performing them. So just from a familiarization standpoint, that could have been a reason what the difference is.
Yes, so you expect a learning effect, or?
We didn't really think of it at the time.
No.
But I remember that there were slight differences between handball and football for certain groups. But I think that was maybe down to their performance level in the sport. It could have been something. At least we qualitatively saw that one of the specifically one of the handball teams among the boys.
But how was the level? Did you have any inclusion criteria regarding level, for instance, or playing position, or training volume, or?
No, so we wanted to actually get the broadest sample, and it was difficult enough to just get teams in. So if we would also had specific levels, I think that would be also just challenge to get a large enough sample.
Yeah.
But of course, that could also have biased certain groups.
Yeah, in the cross-sectional study.
Yes, as we had one team, one boys football team that was national level, training 4 times a week plus a game. Then there was a handball team that were maybe training 2 times a week. And we also remembered first time we were testing them, just in the warm-up, they were struggling with some of the quite normal dynamic movements.
Yeah.
So I had to actually change that and modify that because their coordination and just, I guess I wasn't just used to actually doing that kind of movements. And that team also had quite poor results.
But was it differences between the groups in the cross-sectional studies regarding the level, for instance, or handball players and football players, or?
In that particular group, well, I didn't actually statistically analyze it. We did see a slight difference between the football and handball players. But then at the, I think it was under 16 level, it was either equal or the opposite. But then I also know that I think in handball, at least from around 15, 16, they do have a more structured, especially strength training. So you have like teams training here, usually from high school, I think, but at all clubs I've been, there are certain academies in football where they do have structured and sound resistance training, but I'm not 100% sure, but I think like culturally, at a given point, resistance training and strength conditioning is a bigger part of handball training.
Might be, yeah.
Yeah, maybe that could explain like some of the difference within the groups, but yeah, statistically we didn't actually analyze that.
You discussed the recruitment of the participants with John, so I just jump. This is the number of physical performance tests you have done, and you can look at the different groups, and the sample size is not equal. So why not? Because this is not the longitudinal study, it's the cross-sectional.
Yeah.
And then you could have, maybe you could have increased the sample for the under 18 players. Have you any comments on that?
For the cross-sectional study, the under 18s was by far the most difficult to recruit.
Okay, yeah.
Mainly because there's not a lot of under 18 teams. It's a lot of, or many of the 17-year-olds are more involved in like a junior team or recruit team, where the spread in the group varies with the ages. So we could recruit a team, but perhaps they had 4, 5, 6 that was actually in the under 18 age group.
Yes, because
17 years at recruitment.
Yeah, you recruited teams, not players individually.
Yes.
Yeah, okay. So, but do you think that could influence your results, that groups are different?
Well, of course, particularly for the under 18, we kind of got lucky that this was a very high-performing team, had done a lot of strength and conditioning, and then at least had unfairly improved physical performance compared to the younger parts that maybe hasn't done that much, and their level at the time is mostly from biological development. So I think there might be some sampling bias, well, particularly in the girls where the under 18s are quite a lot fewer than the other groups.
Yeah, so it was much more easy to recruit under 14,
Yeah,
both for boys and girls.
definitely.
Yeah. If you look at the figure 1 from, or I don't know it's 1, but it's from paper 1, you can see that there is a large difference in results for the same physical tests across different studies. Do you have any explanations? Because if we go to the 430 meter and counter movement jump,
Yeah.
then there is for those under 16 boys, there is a huge difference. It is about 1 second in 40 meter, and I think it's more than 30 centimeters for the counter movement jump. Why is there such a huge difference between studies?
I guess there will be several factors that influence these results, and one is probably how they perform the tests.
Yeah,
To know that,
I agree.
say for a sprint test, if you use, well, first of all, just timing equipment will have some influence. Your starting point will have some difference. Say you use 10 to 30 centimeters behind the line compared to 60. That will actually highly influence your performance. Some may just be sample bias, that you involve or recruit a group with a worse or poor baseline value, so then they naturally will likely improve more.
That's a good answer. And because of that, I will move to the equipment. Because you used different equipment for the 30-meter sprint test. So, and I think you use footer gates in Oslo and a contact mat in Kristiansand. And can you say something about the 2 different timing systems?
Let me see if I can remember correctly. So our system, then it is a laser that you break to start the time. While for the contact mat, it is when you release, can't remember if it's the front foot or the back foot.
Yeah, front foot, usually. Yeah.
And at least from experience, it is more error compared error with that kind of method. And we had to actually remove some results because they were just too unrealistic. Like elite sprinter level for the under 13s. I think that's the main difference between them. Because we saw in the results that on average, there was quite a large difference, especially for the way better improvement or performance in Kristiansand with their contact mats, which were unrealistic in, Yeah, because
I can show you, this is, you showed it earlier.
Yeah.
It's the 30-meter sprint test, and the start line is close to you or closest to you.
Yeah.
And the footer gates are placed at 0, 10, 20, and 30 meter. And you say that they started with a split leg position.
Yeah.
But how did they start when they had the contact mat? I guess it was a split leg, but I've tried to draw. So this is the starting position you used, isn't it?
Yeah.
Yeah. And was they also standing 50 centimeters behind the start line when they had the contact mat, or did they place the first foot at 0 meter? It might be a difficult question because I don't know. Did you do some testing in Kristiansand or?
I wasn't part of the testing, but we was down there to go through the testing battery to try and best way at least standardize the methods and do it the same way. And at least from what I can remember, we tried and used the same starting position.
Yes,
But exactly how it was, then I can't remember.
Yeah, the reason why... Oi, something happened. Maybe I need some help. The reason why I'm asking is that you use a correction factor,
Yes,
but I
correct.
will come back to that in a moment. Det ser ut som zoomen er. Because, or you can try to explain the correction factor to me, because you applied, or you can explain how you did it.
So what we did was we first calculated the average difference in performance between age groups, and we ended up using then the average between the under 14 groups. This was then the largest sample with the least variations. We thought that was the most precise estimation at the time. And then we added this correction factor then to the individual results for then the results from Kristiansand.
But then you expect that the girls in Oslo and Kristiansand perform at similar level. And the difference between the groups was added to those in Kristiansand.
Yeah.
But did you check the other groups?
Yeah.
Was it the similar difference between?
There was light difference between some groups, but I think it was at least 2 other groups where the average difference was the same. So boys under 14 as well had, if not 0.0, it was close to it. So there wasn't that too much variation between the groups.
In my drawing, I would I should show how I was thinking, because if I'm not sure if you can make a correction factor as you did. I don't think it will change your results, but it might be other better ways to do it. But maybe we can discuss that later. But my next question is, in the change of direction speed test, you applied another correction factor. And why did you do that? If the equipment is not similar, it's 0.2 difference between the measurements. How can it then be 0.68 in the change of direction speed test? Because it's the sprint test.
Yeah. For the change of direction test, they used, if I can remember correctly, different equipment. So they used timing gates in indoor hall. So also the surface was different. So I believe that both, both the equipment, but also the surface, because what we realized in our gym, it was quite slippery. So I guess if their indoor hall had better friction,
thank you.
that would greatly influence their results.
Okay, so
and likely explain the larger difference.
Okay, so but this is the starting position in Oslo when you use the footer gates. But when you are starting, if you had a contact mat, you will move 50 centimeters when your front foot is leaving the ground. So if that's correct, and I think Haugen and colleagues published a study in 2011 where they compared a contact mat with footer gates, then it should not be necessary to add a correction factor. But if you started, but it depends how you started in Kristiansand. So, but maybe we can discuss that later.
Yeah, right now I can't remember exactly how they did it. I know we tried to standardize as best as possible, and then also the starting position.
Course.
But
and it's challenging when you do testing in 2 different testing sites, and when you don't have similar equipment. So I see that. This is the 40-meter change of direction test, and you state in the beginning the starting procedures and equipment were the same as for the sprint test, but later on, single beam timing gates with infrared photocells were used at the second test. So is it the last one that is correct?
It's the second one, so the Brouwer system,
Yeah, so, but you added a correction factor of 0.68 because of it was more slipper.
Like compared to sprint test, I would assume that would also explain why it was so much greater. I can't remember exactly how the friction was at their place, but I know at our place it was quite poor.
Yeah.
And not everyone, though it was suggested that they bring like indoor shoes. Some came with running shoes, and the friction was quite poor for in some instances.
I see. So then we can jump. And you added also a correction factor to the counter movement jump test. So because you use 2 different force plates.
Yeah.
But how did you calculate the jump height? I don't think there is written something about the empty system. Did you use the software for the empty force plate, or did you use the raw data, or how did you do that?
Good question. I'm pretty sure we did not use the raw data, or they at Kristiansand.
Yeah.
So similar to how we use the data straight from software, I would assume they did the same. Exactly how that software worked, I hadn't actually looked into. So yeah.
And you corrected or had a correction factor of close to 3 centimeters. So was it the same way of calculating the correction factor?
Yeah.
But would it be 3 centimeters if I was jumping 20 centimeters, or if I was jumping 50? Is it okay to have, or correct to have a similar correction factor independent of jumping height? Or did you compare other groups to see the difference?
Yeah, so we did look at like all the groups for each of these tests to see how they varied. And at least for a 30-minute sprint, then overall there was less variation. I can't remember exactly how it was for the counter movement jump. May have been some groups it wasn't that large of a difference. I think for at least the under 14s, where the sample was the largest, it was at least not too different between them.
Okay, yeah. So, but it is challenging when you collect data in 2 different testing sites. So I can understand that. So the last questions on methods is the Kaiser leg press, because you excluded many force measurements, and you had some criteria for exclusion. Can you explain them?
Yeah, so we ended up, because we saw that there was several results that didn't really look valid, because you expect a force curve that is quite linear, but for some athletes it went up and down between reps. So we expected that, because they are informed to like push the maximum on each. Didn't always happen. So we ended up finding one way to exclude some values that we thought or knew were not realistic or not valid. How I ended up at 30%, I think I went through some results and saw that was like some kind of tipping point. But yeah, then we used the 30% difference between what they actually measured than the theoretical, which are the extrapolation of the results. What was the final result we used? Then we had a separate measure which was the velocity at the final rep, which is supposed to be quite much smaller. So with, I think, and I'm not sure if it's been in research, but I know that we discussed that around that time, likely that isn't their maximum effort.
Yeah, and you excluded the force data, but you kept the power data. But it wasn't, you excluded most of the data from the year one.
Yeah.
Yeah, so it wasn't due to the familiarization or something like that. It was because you think that they're not pushing as much as they can in each rep.
Yeah.
Yeah, okay. But the speed, you also excluded if the speed was 0.5 meter per second in the final repetition. That's not a very slow repetition. Why did you exclude those repetitions or measurements?
How exactly we ended up in 0.5, can't remember, but I did also see that most where we see that they have like the correct curve, it's closer to 0.1, 0.2. Yeah, I think, yeah.
Because a maximal repetition in one RM in squat, for instance, I think the speed is then 0.2 meter per second. So you excluded faster repetitions than that.
But from what I can remember, we most often used the percentage variance, and it wasn't that often that when that was below that, the velocity was the only factor. So usually the velocity was above 0.5 when also the difference between theoretical and measure was.
So I'm just moving. Yeah, another thing, because when I read paper 3 first, and when I was reading paper 3, there was something I didn't understand, because if you look at the age, I don't know if you can see the age, but in blue it's the boys, and the age is 16.1 year at T1 and 17.0 on time 2, and similar in time 3. And then I thought 16 years at time point 1 was correct. And what I couldn't understand then was that because the under 14 group, they are 15 years at time point 3. And if you see my figure, you can see that the performance level is similar on time point 3 for the under 14 group to the time point 1 in the under 16 group. And that's because the age is 15 years when you include the, And I understood it when I read your introduction, alla kappa. So, but this is from your introduction, but it's 2 different ages also in your introduction. So I was wondering a bit, because they were similar, had similar speed, similar jump height, and they were 1 year older. But then when I read your introduction, it was...
Yeah, I'm pretty sure that was a typing
an error. So, but you can correct that, because paper 3 is not published.
Luckily.
So, I just have one final question. So, based on both your research findings and your experience as a coach, what would be your main recommendation to a youth coach when it comes to facilitating training that supports individual development, particularly in girls? And maybe it's a wide question, but what do you think?
It's a good question, and probably something that a lot challenges with. Like, as we saw in the trial lecture, that we know that it works, but how to implement it is quite pretty much the real challenge. So at least if you say that you have a team of girls, you're a lone coach, and you have probably way too much to do already, getting in extra work is challenging. If you're also going to individualize it, then problem becomes much worse. So then you come back to like using the off-the-shelf programs that may not be the best for your group at that point. So like the best option is to just hire someone to actually implement and structure this training.
It's not easy
No.
because you have explained it's very many factors.
Yeah.
So, but I'm impressed by the large data collection, and I believe this or your PhD thesis provides important knowledge in a field where there has been a little research, especially on girls. So I have no more questions. So thank you for your attention.
Thanks to the candidate and to the examination committee. The examination committee